All right, so I welcome you all. Today's lecture, we are going to have systems of equation, systems of linear equation. Now, when you start with machine learning, as I said last time, most of us, when we started, it was just the coding. We started jumping on the coding and linear regression. We started calculating loss function and all those things. But what we didn't know was the mathematics behind, this computation, what is actually happening. So today's session is based on linear equation, which is systems of linear equation, and how are we going to solve it? We have a lot of ways, numerous ways that you can use to solve this, but thank God we have computers around. We have better algorithms around that can compute this thing for us within the twinkle of an eye or the blink of an eye. So we are not going to learn about these algorithms like the Gaussian, the Kramers, and all sort of things. The LU lower upper decomposition. We are not going to learn about that because we can write scripts, we can write algorithms in Python to do that. But we just want to understand the geometric interpretation of some of these things so that when you see an equation, you should be or you be able to interpret it and you yourself understand it so that when you write a code for it, you'll be able to know what is happening. And if the results that you are getting does not fit your it doesn't fit what you expect or your expectation, you can redefine the algorithm again, or you can you can modify the algorithm again so that you'll be able to use it to do whatever you want to do. All right, so vectors represent individual data points or features. We've talked about this already, and we use matrices to organize the entire data set. So last time when we started, we said when you pick a data set, the individual features or the column wise, we can represent them using vectors. Yes, Godwin, ask your question. Hello, Godwin. Is there a mistake or you want to ask a question? Hello, Godwin. Can you hear me? Hello, Godwin. Maybe it's a mistake.
Yeah, hello. Hello.
Yes, Godwin, go on. I can hear you. I can hear you.
Okay. Please, can you go on again with the matrix invertible, the invertibility of the matrix? Because I found a question in a quiz, and it was a square matrix, but the determinant was 0. So I actually don't understand a little bit that part. So if you can clarify, I'll be glad. Thank you.
All right. Okay. So, yes, you sent me a message, I remember. And I said the answer was the first choice, which is the matrix must be a square first before be able to find out whether its determinant is equal to 0. Okay. Now, the question, let me explain the question so that you understand. Okay. The question that I posted or the quiz, they gave you 4 options. One of them, the matrix, you get the determinant to be 0. Then the other one, they ask you that is it a square matrix, and the other two were wrong, right? Then they ask you whether that matrix is what invertible, right? Now the first thing is it has to be a square matrix. Now you see, I just decided to trick you guys because I should have put that two things in the same line so that we have it's a square matrix and the determinant is not equal to 0. Do you get it? God, do you understand? But I decided to separate it. So the first condition is that the matrix has to be a square first before you can even go ahead to go and calculate the determinant. Is it clear?
Yes, please. It is clear. Thank you.
Okay. Bismarck, go on. Bismarck,
Yes, please, I can hear you.
but the explanation I gave, is it okay? Because you said it's the same issue you had as Gordon.
Yes. Please, the question asks whether the matrix is invertible or not.
Okay.
So for it to be invertible, as you explained, it first has to be a square matrix, and
Yes.
then the determinant should not be equal to zero.
Zero, yes.
By in this case, it is a square matrix, all right, but the determinant is zero, so that makes it non-invertible.
No, 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 no. You don't get me. I'm saying that the two, you see, we have conditions. Okay. The first thing is that it has to be a square matrix, because if it's not a square matrix, there's no way you can, find it. You can find it, the determinant. You can't find it if it's not a square matrix, right? So the first condition is it has to be that. Once we clarify that it's a square matrix, the next thing is that we can now go ahead to go and find it. So that is where you determine, is it zero or not. So the first condition is that it has to be a square matrix. It has to be a square matrix before you can find a determinant, before you can now go ahead to go and conclude whether it's what invertible or non-invertible.
Okay. All right. So,
Okay.
so first we have to check if it's a square matrix.
Yes, if it's not a square
Then,
matrix, how are you going to find it? You can't find any determinant if it is not a square matrix. You can't find it.
oh, okay, okay, okay.
So you have to, that's the first condition. Okay. Thank you guys. All right. So linear systems in machine learning models. Our first lecture, we saw that we can use vectors to represent all these features. Then when you put these vectors or you arrange them, we have what? A matrix. So when you organize these vectors, you have what? A matrix, right? Now, these concepts are fundamentals to the tasks in machine learning, and you we are going to solve a systems of linear equation where we'll be using linear transformation. We transform one vector to another. Okay, we're going to transform one vector to another. How do you do that? Now, when you talk about a system, just a collection of components that accept an input and produces what? An output. So we have this, you've been seeing this equation over and over again, which A x is equal to what? B. So we put in this vector, we expect this vector to come out. In simple terms, we are translating this vector to this, or we are mapping this vector to this using what? This transformation A, right? So we say that this can be our input, this is going to be our output. But for us to be able to get an output, we need what? A mapping, and that is done by what? A matrix. Now, a linear system would then be a set of linear equations. The word linear there is very, very important. It should be linear. If it is not linear, we can't. It has to be a linear for us to be, or has to be, for it to be described as what? Linear system. So a set of linear equations that receives a vector and produces one or several or no solution. So it receives a vector. Now it can produce one solution or several solution or no solution at all. Now, if you said produce no solution at all, in machine learning, they will tell you that your model is not convergent. It is not going to converge. It's going to take a very long time. Since it's not converging, there's no way you'll be able to find any solution for it. Right. Then you can have several solutions. Now, these several solutions, we spoke about it. That means your model will span it can span a single line, right? That means the solutions keep repeating itself. It's just a multiplication of one value. And we saw a typical example so that if your answer is equal to 2 and spanning this line, on this line we can get something like 4, can get something like 6, can get something like 8. So on this line, this is going to be the span. That is several solution. So if you want to do the calculation, we say that maybe our C1 is going to be 2, maybe sorry, here can be C2. C2 is going to be 2C1, meaning that if you want to get C2, you just have to multiply C1 by 2. So if C1 is equal to 1, okay, then we can get on several solutions or no solutions at all. So let's look at this. Now, this is system of linear equation. The first one is equation 1. The second one is equation 2. Now, we saw this when we were in high school and also GHS, junior high school, where they asked us to solve simultaneous equation. Simultaneous equation, that was linear equation that we were solving, but I mean, that was a different algorithm that we were trying to use, but at that level, we were just dealing with only 2 sets. And today we are going to use only two sets, but we are going to explain using linear algebra to understand the concept. So take your mind or cast your mind back to high school and also junior high school, where we were solving simultaneous equation. So this is a simultaneous equation, but this time we are going to call it what? System of a linear equation. So linear equation. Now with this linear equation, we have scalars. So these are the scalars, and we also have the unknown, which we are going to determine. This unknown, I've already explained it in the previous slide, that the solution can be unique, non-existence, or non-unique. It can be unique, non-existence, or non-unique. That means non-existence, no solution when we solve this equation, or we are going to have several solutions. That means one solution is going to be the multiple of the other. Then a unique solution when we have a solution that exists. So when we plot, you remember when we were in high school, they asked us to draw a graph. One of the things that we did, if it's a simultaneous equation and a solution exists, that means when you have a unique solution, when you plot the graph, you realize that it's going to intersect. So in the intersection is the solution. We're able to find the x, we trace it to the x, we trace it to the y, and we can get our x and the y. So this is when we have a unique solution. When you plot the graph or when you plot the curve and you realize that they are parallel to each other, that means there's no way they are going to intersect anywhere in space. So no solution. No solution is going to occur here. So here we have no solution. Here, you realize that they are not intersecting, but one of them is lying on the other. It's like one of them is spanning. So it's just a continuation of the other one. So this is where you have what? Several solutions. So you're going to have infinite number of what? Of solutions. So these are the 3 conditions or 3 ways that when you are solving a linear system, in terms of solution, either you're not going to have any solution at all, either you're going to have several of the solution, or you're going to have what? A unique solution. So a unique solution means that our line or our lines will intersect somewhere in space, and we can trace it to the individual axis to read the solution. Now remember, this we are using 2D, 2 dimension. But when we are dealing with features, where the features, for example, if you want to come up with a machine learning algorithm that is going to help classify breast cancer, and breast cancer has a lot of features. About, I don't know, but it can get to 10 or 12. If you look at it, you see that you have more features. So your unknown is going to be a lot, which is about 12 of them. Now, if you have 12 unknown, that means you are in a higher space, which is hyperspace. And this hyperspace, I can't draw it. But if I have let me switch to this. So if I'm in a 3D, with 3D, we all know 3D, this is my 3D, right? So this is my Z, this is my Y, this is my X, right? Now, if I plot a line here, I mean, it's going to be quite a little bit complex for me, but let me try to just plot. So, three lines, let's assume there's an intersection here, they are intersecting over here. First, we send it to the plane, which is the base plane. Then, we try to draw a line, then we draw one off here, also or draw one over here, okay? So here, this is my X, this is my Y, this is my Y, this is my Z, right? So if I have system of linear equation where, let's assume I have my scalars here, but I have my X, Y, and Z over here, okay? In this space, which is this 3D space, when we plot the curves, they have to meet somewhere. When they meet, we trace them to the individual axis and read the results. And that is the solution. But human beings are limited. How are you going to plot this? Even in 4D, how are you going to plot this even in 5D? That is going to be complex for us. So we leave these things for computer systems to do. People have developed algorithms. And one thing about mathematics is that if it works in 2D, you are confident enough that to work in 3D, to also work in what? 10D, right? So you see how we extrapolate from one dimension or two dimension to higher dimension. All right. So if the lines intersect, I've already explained this, then we have a unique solution from, we have this equation, right? I've already explained that these are scalars, right? And the solution that we are looking for, that is the X, and the B is what? Another vector. So yes, last week we learned about transformation, and I did explain it in the first slide, that here what we are doing is that we are transforming this vector to this using this transformation. We are transforming this vector to this using what? This transformation, right? And last time we learned that we can use inverse to be able to do this calculation. How do you do that? We learned that if we can find the inverse of this matrix, we multiply by this, be able to what? To get this. Now, in actual sense, what we are actually doing is that we are mapping. Okay, we are mapping this vector X here to this vector B. So let me give you a practical scenario that you are in school. Okay, this is maybe your house, your home, and you are going to school. So this is, let's say, your school, right? Now you are moving from here to here. So we need a matrix to do that, right? So moving from your home to the school, we are doing a transformation. Now, for you to get back, we have to find a way for you to get back. If you get to the school, you are not able to get back, it means our transformation, right? This transformation is not, I mean, when it maps it, let me put it like this. This transformation, when it maps it, is not going to get you to your school because it's not going to return you to your house, right? So we saw that when it happens like that, it means your determinant is equal to 0. Definitely, there's no way it can return you to your home, right? So if you look at what we are doing over here, what we are saying is that, I just want you to see it because I will use that one to explain a lot about determinants. What is happening here is that although we are looking for X value, but in actual sense, we are taking B back to X. It's like we are taking you from your school back home. If we use the inverse, we are transforming X to B, but for us to be able to get our X, we need to carry B back to X. That's why we are finding the inverse. So I'm taking you from your school to your house. That is what is happening over here, because in actual sense, because we are transforming x to b, we can also transform b to x. And once we do that transformation, we know the value of what x. I believe it is clear. So if A represents a linear transformation, then we want to find a vector x that when we transform by A lands on B. Now this statement is very, very important. That is what I've explained to you, but I will use graphical interpretation or geometric interpretation to explain it to you. Now, if we represent A, which is A is just a linear transformation, or A is a linear transformation, what we are doing is that if you want to find our unknown, this, what we want to do is we want to transform this vector that is going to land on x. That is another way I say that how do I get this back to this? Because if you can get this to this using my A here, I can also get this to that. And that is what we are going to use in Cramer's rule to be able to transform the targets, which is the target value, back to the unknown. Once we can do that, we can calculate the value of our unknowns. Now, for two vectors to intercept somewhere in space, they need to be linearly dependent. Now, you see, we've been stressing this over and over again, right? That when you talk about a vector space, there are certain things that last time we spoke about, that when you have a vector space, any vector space can be expressed as a linear combination. Now, this linear combination, we have to make sure that they are what? Linearly independent. That means we should not have a vector that can be expressed in terms of the other. And that is something that we try to eliminate, right? So for these vectors to intercept, and I've shown you a geometrical interpretation, for them to intercept somewhere in space, first thing is they have to be linearly what? Independent. They have to be linearly independent. We see that known as the column space. This we spoke about it, the column space. The columns, they have to be independent. They have to, or else the solution will be a problem. The determinant of a matrix that has these same vectors for columns cannot be zero. Okay, so if the columns are linearly independent, there's no way our determinant will be zero, right? Yes. So a practical scenario, an example is if I have here is 2, here is 1, right? Then I have here 4, and I have here 2. You will tell me that if I multiply the first column by 2, I get a second one, right? So we say that this column space is equal to 1, right? Because if you look at this, okay, so when you multiply this by that, this by this, okay, you will definitely, if you multiply this by 2, you multiply this one by 2, you get this. So the determinant, you tell me that is equal to what? 0, right? So 4 minus 4, which is equal to what? 0. So you realize that these two vectors, which is because here this is a vector, this is a vector, these two vectors, they are linearly dependent, because this one depends on this. So this condition, okay, will not be satisfied, because they are linearly dependent, we are going to get 0 for the determinants. Okay. Now, for us to get a unique solution, that means it has to be what? Linearly independent, and the determinant should also not be what? 0. Okay. So let's consider this. Now, if I ask you guys to solve this using simultaneous equation, you guys can do that for me, right? So when we're in high school, what we were told to do is we try to eliminate one of the variables whilst keeping one. So you tell me that, okay, we can multiply, if I name here equation 1, if I name here equation 2, I'll multiply this by 2, or else I'll maintain this. So if I multiply this by 2, what I'll do is I will now try to what? Subtract. So when I subtract, I can get rid of this, then I'm able to solve my x1, right? Yes. Now, if we put this one in a matrix form, you first have to check these two columns. The column space will definitely be equal to 2 because there's no way I can express any of these vectors in terms of the other. So they are linearly what? Independent, right? Now, what we do, we check the determinant. If the determinant is equal to 0, then we can't do anything. But because even if I look at it over here, or by we looking at it, you see that they are linearly what? Independent. Determinant here by finding it is what? It's not equal to 0. It is equal to 3. That means we can go ahead and say that this system of linear equation over here will have what? A solution, which is a unique solution. Okay, now let's look at this matrix. Now, if you look at this matrix, you will tell me that the same thing, if you multiply the second column by some scalar, you are going to get the first column, right? Why? This one shows you that these two columns, they are linearly what? Dependent. So the column space will definitely be 1 because it is only 1. Why? Because we can get this from here. Now, when we check the determinants, we are getting 0. So that tells you that if I should plot this somewhere, you see that if I plot this, the two vectors, they lie on each other. These two vectors lie on each other. So what is actually happening? What they are, the vector collapses. It collapses. Once it collapses, I mean, there's no way you can do anything about it, okay? Because everything goes to 0. And we say the vectors are linearly independent. The angle formed between them is also what? 0. And determinants, anytime we talk about determinants, last time we spoke about it, we are talking about area. We are talking about what? Area. But here, because we are getting 0, this is what? Spanning what? A line. So there's no way we can find anything over here, right? Now let's take this equation. So we have this equation, which is the one that we calculated, and we realized that we can solve this equation. Why? Because the determinant is not equal to 0. Okay. So let's look at this. Now, when I ask you guys to solve this using simultaneous equation, you can all do that. So I'm giving you guys 2 minutes. Solve this using simultaneous equation. Then you type in the answer. Okay, yeah, let me create a poll. So I'm giving you guys 2 minutes. Do this quickly and before we use our matrix to do that. So 2 minutes. Start. So should it be a quiz? Should be a quiz. No, it should be a poll rather. Right, so we type the answer, the solution. So x1, x2. All right. So 2 minutes. All right, so majority of you are saying the answer X. I'm coming in a minute. Okay, so majority of you are saying the answer is equal to 2 and 4, right? All right, so we'll find out. All right, so here, what we can do, or what we are going to do, is we are going to use linear algebra instead of using simultaneous equation approach. So here, we take our scalars from the equation, and we have our known, then we have what? The targets, which is where we want to, the B, which is where we want the transformation to land. And I explained to you that here, this is going to transform, the A is going to transform the X to this place. So in other words, we can also transform this back. So once we transform this one back, it's the same thing as we transforming. So if we can get back, the value for us to get back is the X1 and the X2. That is simple. I just want you guys to take this. If you want to solve it, the matrix is going to transform this to this. So instead of us transforming this, we can transform it backwards. So once we do the backwards transformation, these values is going to be X and X1. All right. Now let's look at it. So this time we are going to look at it from geometric interpretation. So pay attention and let's try to explain it together. All right, so let's look at this. Now, if you look at it, I have a lot of things happening here. The first one is my individual basis. So I have my I. The I, we saw it is what? 1, 0, right? So if you plot it, 1, 0, which is this direction, then my J is what? 0, 1, right? If you plot it, this is it. Then I have my 2 column vectors from the matrix. Remember, this is a vector. This is also a vector. Remember that. So this is my column vector. This is another column vector. So we say here the column space is going to what? 2, right? So when I come here, I have the first one, which is -5, -4, right? So -5, -4, it lands here. The other one is what? 1, 2. 1, 2 also lands here. Then our B, where we are transforming or mapping to, that one 2 is -2, -4, -2 what? -4, right? Now we have this. We have done our plotting. The next thing is, how do we, interpret this so that we can get our X1 and X2? Okay. Now, one thing we can do is we can use determinant to do that. Now, remember last week that if you have a determinant, what we're actually doing is that it's just area, okay? That is a space, which is an area. So let's look at this basis, individual basis. Now, this forms a parallelogram. A square is a parallelogram, Okay, so this forms a parallelogram here with all sides being the same and the angles equal to 90 degrees. So formed by this basis. Now what can I do? I can transform this individual to a different vector or different space, and when it happens like that, I'm using this. So once I use this on this 0, 0, 1, then I use it on the I, which is 1, 0. You will tell me we learned it because here will be 0 is going to give you 2, 0, because we learned that if you are using the individual basis, this will give me this. Okay, then if I have the other one, oh sorry, here is 2. Here's 2, sorry. The other one, which is 2, 0, 0, 2. Then I have 0, 1 over here. This one, without doing any calculation, I know my answer is going to be 0 or 2, right? So if I plot this, this is what I'm going to get. Now you see that the area has increased, right? It was this. Now it has increased. What has happened over here? The transformation has changed our area to a different area. And that transformation, which is doing that, is also equivalent to another factor that is called determinant, that we can call determinant. So when we have the determinant, it's the same thing like you multiplying this area, this small area, by that determinant. This small area by the determinant, okay? So if we can find the determinant of this, which if you do, you get 4. In actual sense, if I go back to my graph, in actual sense, if I go back to my graph, if you look at this, what are we doing? We are spanning this. So if you look at this area, okay, if I multiply this area, because it's 1, I'm going to get 1. So if I multiply by a factor of 4, that means I've increased it all the way to this place. You get it? Because this is a square. Okay, so the area is equal to 1. So if the determinant is a factor that scales, okay, scale the area or stretches it, can also flip it. Okay, that means if I multiply this, it's going to get me this. Now, one thing about the determinant is that it can also be negative. When it's negative, it tries to flip the area. So flipping, you understand flipping, laterally inverted. Okay, that means you are standing in front of a mirror. So you try to flip. The left becomes the right. The left is what? Left, right? Now start all the things we were taught in high school, those things, okay, bring them here so that we're able to appreciate determinant, how it's able to, flip and stretches, strengths, all these things. So when you do machine learning, deep learning, those things, and you just have it at the back of your mind that you are flipping spaces and shrinking spaces and stretching spaces, and that is what you are doing in order to what? To get the results that you are looking for. Okay. All right. Now the same thing over here, I can also have another transformation, but this one I'm using or multiplying the thing by half. So in actual sense, I'm going to decrease it. I'm decreasing it. Okay. So you see, you can expand it or stretch it. Can also what? Shrink it. Can also shrink it. Last week we saw that this is what is the determinant, because that the scalar that represent the change in area inside due to what? Transformation. So when you are transforming one vector to another vector, okay, definitely you are going to change in that area. That change in area is called the determinant, and we are going to see practical scenario. So let's look at this. We saw these two last week. So I have two vectors over here and I have a transformation here, right? So let's look at the two vectors. I've done my plotting. G goes here, L also goes here. Now this is a parallelogram, right? So when I transform any of them, when I transform this, the J by this, when I transform the J, if you understand, then I transform the L, it's going to flip it. So there's a flipping over here, right? So here, what is actually happening is that when I find a determinant, I'm going to get negative because I said negative determinant flip. So flip your area, right? So here, if you do the calculation, you get -2, okay, which is what? Flipping your area. Is it -2? It's -1 rather. Yeah, it's -1. Sorry, not -2. It's -1. Like -2, I was expecting the area to expand, but it says it's -1. Yeah, so it's -1. So -1 is let's flip it. So laterally inverted. Okay. All right. Now we are now back to our question, which we saw this -5, then -4, then 1, then 2. Then we said we want to move this x1, x2, want to move it all the way to what? -4, -2. Is it -4, -2, or -2, -4? Let me verify, please. Okay, -2, -4 rather. Right, -2, -4. All right. -2, -4. All right, so let's look at something here. Now, when we pick any of these vectors, you are going to tell me, oh, let's even pick this. Let's pick this vector. You pick this vector, it can be expressed as what? X1, right? Then 1 is 0. You agree? Then plus x2, right? Then 0, 1. You agree? I believe now you are okay. So what can I do here, or what can we do over here? Now this, you remember last week and last 2 weeks, we said that when we are doing the transformation, it's the same thing like doing a transformation on the basis. Because when you transform the base, because each vector that you are trying to transform, it can be expressed as, linear combination, right? So I can transform the base. Once I transform the base, it's equivalent to you transforming the vector. And that is what I've expressed over here. If you look at this, x1, 1 is 0, x2, 0, 1. So if I put a transformation on the basis, it's the same effect, because when I get it, I can multiply it by my x1 and x2, and I'll still get what my answer. Because any vector at all in this plane can be expressed using what these bases. All right. So once we have that, what we are going to do is we are going to try to, have some transformation over here, which is the calculation that we are about to do. So pay attention here. Let's pick the first one, which is this, on this axis. Now, when on this axis, now this x can be any arbitrary number. Okay, so I decided to pick anything over here. So here it is 2, 4. Okay, but that is not the actual value. Okay, we are trying to explain something here. So here, when you pick this vector to this direction, we can form an area with this, the linear base. When we form an area with the linear base, what are we doing here? That is a transformation we are doing. We are transforming. You understand? So the transformation we are doing over here. So this, we can calculate this area. And this is what? A parallelogram. What is the formula if you want to calculate the area of a parallelogram? What's the formula? What's your formula? I think it's 1 over 2. Is it 1 over 2? A plus B times H, or what? Or it is, I think, A plus B, but I think it's A times the height, eh? Yeah, one of the parallel side times the height. Please, tell me, the formulas skip me small. This is for trapezium, but the parallelogram is, I think, is the base. No, this is the base. It's one of the parallel side times the height. Is it correct? Okay, so okay. So A times B. So base times height. Okay, that is correct. Base times height. Okay. So we take the base, then we have the height. Okay. So base times the height. Thank you. All right. So the base times the height. So what now here we can pick, this is what we are going to take as the base because we can't calculate this. So this is the base. So the base we know is 1, right? What is the height? The height is this from down here all the way to this, which is what? Dot S2, right? So that's my area, which is A1. A1. Okay, so my A1 is 1 times what? X2. Now, what is my X2? We'll find out. Now, if you should multiply this, we will get something like this. If you are doing the actual transformation, then it's going to be minus 5, minus 4, then it will multiply with x1, right? Then plus x2, which is 1, 2, right? So we have something like this. Now, let's look at this. Now, what are we doing over here? So here, as I told you, we are going to transform. Now, let's pay attention to this. I'll come back to this formula for you to explain something when you go to the Cramer's rule. Okay. Let's move on to the next one. Now, when you find it, this is you've seen it. So we call it the sign area. Okay. The reason we call it sign area is because the determinant can be negative as well. Okay, can be negative. It's not always positive. It can be negative. So that's why we call it sign area. Now, let's move on to the next one. Here, we are using the J. Okay, we are using the J. Now, let me put this one again here so that we see what is happening. Negative 5, negative 4, plus x2. It was 1, 2, right? I think I'm correct. 1, 2. Correct. Now, here too, we can do the same thing. Here, our height is going to be this. Is going to be our height, and our base is going to be this. So our area, which is A2, is going to give us the base, which is 1, still 1. Then the height, which is what? X1, right? X1. Okay. So now we have this. We can now try to extrapolate and find a way to be able to solve our equation, which is this. Now, as I said, I will come back to these equations again, why we are expressing this way. All right. Now, we are looking for this equation, minus 5, minus 4, 1, 2, and we have x1, x2, which goes all the way to minus 2, minus 4, right? Now, remember I told you that when you have a, x is equal to b, we are transforming this to this. We can also transform backwards. We can do that. So the best way to do this is, remember, if we are multiplying this, to do this transformation, it's the same thing as I did over here, which I said I'll get back. This, right? So here we are doing the transformation. Now here, what are we trying to do? We are going to get a b over here, which is b1, then b2, right? Now what is happening here is, what we are saying is, when you pick each of these vectors, okay, which we are transforming with the matrix to this, we have a portion of this in these calculations. These calculations, we have a portion of the b1 and the b2 in this. So for us to be able to do this, we can also use the same area formula that we are doing in order to be able to get our x1 and x2 back. I told you that we are transforming from x to b. We can also go the other way around. And that is what has been done over here. So what is done over here is that we are trying to find out which this part, the -5, the -4. Instead of us using x, we are using this. Now, why are we using this? You remember I said that we are transforming from here to this place. You get it? We are transforming from here to this place. In other words, if I'm also here, I can also what? Get to this place. So what I'm doing is that I want to find my way back home. In order to find my way back home, we said to use the inverse, but this time we are not going to use the inverse. We're going to use the Cramer's rule. Okay, so what we are doing here is, if you look at the direction of this, we don't know that the direction of this, where this is pointing towards. We don't know. You guys did a calculation and you had what? 2, 4, right? You had what? 2, 4. So if you should plot this, the direction will somewhere be up there. Okay. So how am I going to, turn this or flip this for it to be able to point in this direction? So first, because we can construct this vector using this transformation, we multiply this, we multiply that. It's the same thing like we turning it to face that direction. You understand? So as I gave a practical scenario, you went to school, you want to return home. So we have to make sure we turn you so that you can now, get back home. So what we do is we pick the -5, -4, and pick the b, which is also -2, -4, -2, -4. We pick this and we calculate the area. We can find the area. How do you find the area? This is also a parallelogram, right? We can find the area. So which one should be our height? Which one is going to be? So if you pick the basis, so let's pick which one can be this or that. You can calculate any of them for me, the determinants or like the Euclidean distance, right? So once we know the base, the height, we can calculate it ourselves. Now, that is what Cramer, or I don't know how it is pronounced, but I think that is the right word. That's what Cramer came out with. He came out with a rule that we use to be able to do the calculation. So here, as last time I did explain, we have our vector. What actually doing is that we are just turning, switching, shrinking, flipping our spaces or our grid. There's nothing intelligent over there. Right. So let's look at this. Now let me skip and draw this quickly so that we're able to see this. Okay, so when we pick our vector, the transformation, we had 1, 2. Let me zoom in. Let me zoom in. Let me zoom in. Okay. Okay. So we had 1, 2, right? So which is here, which is this direction. 1, 2. Then the other one, we had -5, -4, right? So -5, -4, we come all the way to, no, I'm lost. Let me clean it, take it again. We come all the way to this place. Bismarck, go on.
Please, I think the first vector is 2, 1.
It's 2, 1 rather, not 2. Okay, okay. Let me change it. All right, so here is 2, then 1. Okay. Then here is -5. Okay. Then here is -4. Okay. Now, this is, I mean, I wanted straight lines. Oh. I wanted straight line, I wanted straight lines. I don't know whether straight lines. Okay, let's use straight lines instead. But I want you to see what is happening. Okay. 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 So let me use this. So this we said is 2, 1. Oh, all right. So the other one, 2 is 5, 4, right? Okay. We have this now. Now, if you look at this, we can have an area out of it, right? So let's draw the other one too, which is -2, -4, which is over here. -2, -4. Okay. Now the area for this, if you want to draw that, I don't think am I making a mistake? No. I think my drawing is wrong, right? This thing. Oh, my diagram is, there's nothing parallel here. Wow. Oh. No, no, my diagram, I'm coming, let me find out properly and draw it well. Like, my diagram is bad. Okay. So this, let me clean this, let me delete it. This is correct. Okay. Let me also delete this one. Okay. So I think it will shift from here all the way to this place. Yeah, let me delete this. Then it will continue all the way to this place. Yeah, yeah, I'm supposed to do it like this. Yes, mistake. Okay, so when you pick the vector, which is the vector the -5, -4, then 1, 2, this is the area. Okay, When we find the determinant, we had what? 3, right? We had 3. Okay, now the second one is over here. Okay, so what we are going to do is we are going to pick this, which is the first one, which is the -5, -4. Okay, I'm going to pick this and find out the direction that we are supposed to turn for us to be able to face this one back. Okay, so here we were going to pick, let me zoom out, let me go on another. All right, so here we are going to draw another area here, which this will go, I think to go this way. Am I correct? It will span 1, 2, 3, 4. 1, 2, 3, 4. All right, so it's supposed to be somewhere here. And this one to span 1, 2, 3, 4, 5. Okay, so that is correct. We also span this way. All right, so this is what is going to happen. Okay, so here, here, here. All right, then we also do the same thing also for this. So this, until we come down, then we go up. So here, we go this way, move 2, then also continue this way. All right, okay. All right, now this is quite messy, but just try to follow. Okay, so here is 2, 1. Okay, then this place is -2, -4. Okay, so let me go up a little bit. All right, so what is actually happening here now? This one is our area. You get it? This is our area for the matrix. We had the determinant that is equal to 3. And we saw that if you have a determinant which is equal to 3, that means, if you want to find the area, it's going to be a modification of that. You're going to scale it, right? So what we are going to do is we have a one vector over here. We also have another one over here. Now this is where we want to get to. This is where we want to get to. We don't know our x. We don't know our x1. We don't know our x2. But I explained to you that it's like we getting back. You understand? So what am I going to do? What we are going to do over here is we are going to transform our this. Okay, we are going to transform this. We're moving from here all the way to this place. Then I'll carry this and I'll put it over here. You guys get it? So where am I? I'm here. This is the place that I am. Okay, so we started from here and we are now here. Okay, now if you do the same thing for this, that one too, we are here. Okay, so that one we here, but look at where we are landing now. We are here. Okay, so if you look at it, you are supposed to go here, then continue, but it's like we can't do that. So we are here, then we come here and look at where we are landing now. Okay. Now, if you look at it, you will tell me that, we are almost like on a straight path, eh? Are we on a straight path? Almost. Okay. Yes. It's like we are almost in a straight path. Okay. So what we just did is wanted to know the contribution this vector and this vector is going to do, is going to give or produce for us to be able to get back to our x1 and x2. I gave you a practical scenario. It's like when you do the transformation, we can also transform back from the b to the x. And the x1, we use it to multiply this. The x2 used to multiply this. In other words, we can do the same thing for this so that we can get back to our x1 and x2. Okay, let's switch and go and look at the mathematics behind this. All right, so this is the mass. Now, if you want to find the area, so this is our original area. Okay, this is our this is the new area, and this is the original area. So if the area of the original parallelogram was this new shape will have an area of this. So this is our new area. Now this is our original area, which we can find that. Okay, that is the determinant. Okay, so if you want to find the x, any of the x values, it is our new area divided by the original area. The new area divided by the original area. Now this one is trying to tell you that how many columns, when you do the calculation and you get any value, it tell you how many columns should we move so that we can be in that direction. So let's take this. Now, when you pick, this is our vector, but no, this is not our vector. This is our matrix, -5, -4, then 1, 2, right? Now, I want to know the contribution this part, the first column, is having on this. Okay. We already know the area of this. We calculated it. We already know that. Okay. So this is like a new area we are going to find, and that is what I showed you guys. So let's go and find out. All right. So if you take the x2, okay, so here this is our column 1, this is our column 2. Okay, so if I want to find x2, I need to replace the second column. I need to replace the second column by my targets, which is the -2, -4, and I showed you here. Okay. So what we did over here, was we picked this and we wanted to find out the area, the new area formed by this. Okay, so this new area is what we are going to find. This new area is what we are going to find. Have to be quick. Wow. So that is that, and you find the determinants, you get 4. Then the same thing here. If you look at it, here's also column 1, column 2, right? So if you want to find column 1, we replace the whole column 1 by our B, and we can go ahead to find that. So the answer is 2, 4. Okay, 2, 4. So what is the implication? It's saying that if you are getting 4 for this, that means this, let's go and check in how many columns are we supposed to move so that we're able to get into the direction of this. Let's find out. Okay, so the direction is this. The direction is here, right? Okay. So this is our direction, which is over here. Okay. So, and this one is over here. So how many? 1, 2, 3, 4. Okay. So that is 1, 2, 3, 4. I think it's 1, then 2, then 3, then 4. Then we are here. Yeah, I think so. Okay. So that is that. Yeah. Then another one we have 2. So we have 2. So here, if you look at it, this is the direction. Okay. So if you should span and continue in this way, okay, this way, let's go to the top, span to continue in this way. Okay, that one too, you are going to move to pass here. So we move 1, which is 1 here, sorry, 1 here, and 2, they'll also be in that direction. Okay, also be in that direction. Okay, so the x1 is telling you that, I mean, this is the x1, so we move 1, 2, 3, 4, we must be in this direction. The x2 move 1, 2, sorry, move 1, 2, and we also be in the same direction. Right. So that is that for that. Okay. All right. So let's be quick so I don't waste time. So the Cramer's rule is what we just saw, and this is the formula. Okay. When you go through the slides, you understand it. So if you want to find whatever, so if it is x1, x1 is determinant of, I mean, which is this. So here, this is what you are going to replace. So the value determinant A subscript I is the matrix formed by replacing the ith column of A1 with the column vector B. Okay, so if you want to find this, then you need to replace the first column by the vector B, and I did show you over here. Okay, if you go back, you saw it over here. Okay, so if you want to find x1, replace the column 1 with this. If you want to find x2, replace what? The second column with the vector B. All right, so that is that. Now let's proceed and okay, so one thing you can do is that you can also want to check. All right, so we've gotten this. We can also find a way to verify. To verify what we do, we just have to multiply whether indeed this transformation will lead us to what? To this. And that all has been done over here. So if you do it, you see that this will multiply this, get minus 10 minus 8, this will multiply, this get 8 and 4. If you sum it, you get what? You get 2. So you see, instead of us moving from here to this place, we can move backwards. Okay, we can move back to this. And that is what I did explain. All right, so let's talk about linear regression and we can close the chapter. So linear regression is a method for modeling the relation between two scalar values, the input variable x and the output variable y. Okay, so the model assumes that y is a linear function or a weighted sum of what? Input variables. So you have this. All right, now we are going to use matrix to do that. So once you have your function, it can be expressed like this. We call these values parameters. Okay, so in deep learning or machine learning, we say they are parameterized. Is it parameterized or parameterized? That's the way they use. All right, so these are values, scalars. They are numbers, scalars. Remember? All right. So this, if you are dealing with multiple input variables, that means more than, I mean, here we are dealing with only one feature. Okay, so we are dealing with only one feature. So for example, if you are talking about, let's say, maybe student performance, you want to know student performance and maybe the game that they play. So here the performance and the student game, they're just two features. So one is the target, the other one is the variable. If you want to deal with multiple of them, this is what we do. You will see it next week in the lab. So objective of creating a linear regression model is to find the values of the coefficient B, which are parameters, that minimizes the error in the prediction of the output variable. Okay, so it's going to minimize it. The reason being that we have noise. Any data at all that you have, they all have noise in them. There's no way you run a model, you get 100%. No. Okay, you will never get 100%. Why? Because we have noise. Okay, so what we do is that we try to minimize. Okay, so this is our actual value. This is the actual. So the y, we call it the actual value, right? And the y with the hat, with the y hat, is the predicted value. So we say machine learning. Machine learning just boil down to one thing. The learning happens over here. Okay, so what we tell the model to do is that when the error is too much, we penalize the model then to learn. Okay, if the model do any guesses is correct, don't pay attention to the correct answers, because if it is correct, that's not what we are paying attention to. But anytime the model guesses wrong, then we need to penalize it. Okay, and that is where the learning happens. So how do you do this in using linear algebra? So here, how many features do you have here? You tell me there are 3 features, right? So this is what? F1, then what? F2, then what? F3. Then this is the unknown. We don't know. This is what we're going to look for. And these are our targets. Okay. So the same thing as you saw, instead of moving, transforming this to this, okay, we can transform ourselves back and be able to get our x1, x2, and x3. Remember, we are still using vectors and matrices, so the properties of vectors, the properties of matrices, they still apply over here. So here, if you look at it, okay, so here, if you look at it, we are using what's known as the linear least square method. Okay, so here where we find the difference, we sum, the errors. Okay, then we find the difference, then we square. This we'll talk about it, but I want the linear algebra on. So let's get there. All right. Okay, now all this equation that, the linear square that you saw, we have a generalized equation that we use, which is the normal equation. This is derived based on calculus. Okay, we'll see it the next time that we meet. The next internship. Okay, where this is the normal equation, and this normal equation can be written in the form ax is equal to b. Can be written like this. Okay. All right, so where our theta is the vector that we are looking for, the model, then this is our target and this is our feature. Okay, so this is what we are looking for. This is our feature, what we are looking for. Okay, all right. All right, so the normal equation is familiar to this, as I said. So our a is equal to this, then our x is this, and our y is this. Okay, so when you go back, you look at it again, you will see that he's saying that this is our a, okay, and this is what our b. Right, so it boils down to the same thing, right? Okay, so we are going to use what? Systems of linear equation to solve this. Okay, so let's have an example here. So here, suppose that I have a data point. So these are my, data point, and this is my variable, this is my targets. Okay, so here, as you saw earlier on, we can write it in this format, which in a matrix form, we have something like this. Okay, so here's like a line, straight line. You saw what previously we had what a straight line, so we can write it this way. Okay, which we put in a matrix form, we have it like this. Okay, so let's assume this is what. Now this one that you have over here, we will talk about it why we have the one over here. Okay, but in a matrix form, this is what we are going to have, because if you look at it, the data points span or start from 1 all the way to m. So we have this feature and this one. So I have feature 1 here, and what feature 2 over here. But this is all 1, 1, 1, 1, 1. And let's look at this. Then this is what we are looking for, and this is our target. So remember what we just did. So the column 1 represents the constant term. The column x, which is this one, represent our x values. And this is the unknown, what we are looking for. Okay. Okay. So in linear algebra, regression regression model is written as we have this, okay, which is the same as this. Do not get confused, because the same thing that we are doing over here. Okay, it's the same as this. Okay, so here our x is just what our theta, then a is what our x, then b is what our y. That is what we are doing. Okay, so this can be written as, simple linear equation, which is a straight line. Okay, multiple of them. So here, if you want to write this, then you can have y is equal to some 1 plus x1. Okay, then So here's y1, and y2 is equal to 1 plus x what? 2, right? Okay, you go all the way to what? Ym is equal to 1 plus xm, right? So if you in the matrix, that is what we have over here. Okay. Okay. So the constant term is essential because without a constant term, the model is forced to pass through the origin. Now, that is something that is very, very hard to come by because in real life, there is no way you, or even I remember in high school when we were tasked to draw, I mean, line of best fit, hardly will you get all the points passing through us. I mean, all the points passing through the origin. No, it will not. They are scattered. So if you don't bring the one over there, I mean, our model is going to perform so badly. It's going to perform so badly. So that constant term over there is very, very crucial. Very, very crucial. So without a constant term, we end up getting something like this. Okay, so that one is going to make the line pass through the origin. Okay, it's going to make the line pass through the origin. Now, if it makes the line pass through the origin, you are going to tell me that it's going to be something like this, right? So it will be difficult for us to move up and down. Okay, we can only slide over here. We can only slide over here. All right, it's going to it's going to be difficult for us to move up and down. But in real life, because we are not dealing with a perfect data, we have noise, we have a lot of things. Okay, so that constant over there helps us a lot. Okay, so as I said, we can only slide along one direction, we cannot shift up and down. But real life data does not go through the origin, so the fit becomes what? Poor. So that one over there is very, very important. Okay, so let's proceed. So we have the matrix. We can represent the matrix with the vector, as you can see. So the V1 is the feature one, which is the constant term, and the V2 is okay. All right. So what we are actually doing here is these two vectors is going to span a plane. Why? You can tell me because of what? It is two dimension, right? It's two dimensions, so it's going to span a plane because it's two dimension. Okay, so this is one dimension, this is another. Um, so it's going to span a plane. Okay, yeah, because I will need to describe it. Any prediction vector that we produce must lie in the plane. Okay, any prediction that we do must be inside the plane. Must be inside the plane. Okay, but actual data vector, why may not lie in that plane. It may not lie in that plane. So what we do, then we have to do projection. Okay, we have to do projection. So a practical scenario, if this is your plane and this is the actual data, your actual data may not lie on this plane. So what do you have to do? You need to project on this. Remember we did projection? Okay, so we want to find out what amount of this actual data is in this plane. Okay, what amount of it? So that is what we have. Okay, so we are projecting our data onto the plane. Once we can do that, then we'll be able to find the error. Okay, once we can do that, we'll be able to find the error. So you see that now we are using only linear algebra over here to be able to what? Determine our error. Okay, determine the error. So we are just doing vector projection. We are projecting one from or one column space or one space what to another. Okay. So when we do that, say this gives us the condition. Now this is still the normal equation. So when we do, if you go ahead and do the calculation, okay, we've done the vector projection, you end up getting something like this. Okay. When we do the expansion and rearrange it, we get the normal equation. Yes, Albert.
Yes, so please, can you? I didn't really get the projection parts.
Okay.
Yes.
All right. So what I'm saying here is we have each column of Z is a vector in this dimension, right? But what we are doing here, we are putting it in a matrix form. Okay, we are putting in a matrix form. And remember, I want you to remember that this is like a point. Okay, because it's M, this one is M, is like a point. Okay, this is like a point. Okay, so if we should draw it in this dimension, which is this Cartesian coordinate, but it's not going to be two, it's going to be that dimension. You end up getting a plane. Why will you get a plane? Because you have 2 points. Okay, so if I should translate this to a Cartesian coordinate, I'm going to have 1 point here, another point over here. Okay, so if I'm moving from the origin, okay, I'll get a plane. Okay, I'll get a plane. Now, when I get a plane, we say that this any data that we expect must also be in this plane. Any data at all must find itself here, right? But actual data in real life, they don't care. You understand? They don't care. So that is why I said where the learning comes. So you are learning, the model is learning. Okay. So we are telling the model that anytime we do projection, okay, you have to find yourself over here. So what about if you get a point that is over here? We need to find a way to project it onto the plane. Okay, by we projecting onto the plane, what are we measuring? We are measuring that amount of that vector, okay, because the projection just telling that what amount of that vector can we find inside the plane. That is where we calculate the error. The error comes in. Okay, that's why we keep calculating the error. Okay, so we keep calculating the error. Now, if you get the error here to be 0, that is a unique solution. But in real life, you're not going to get the error to be 0. Okay, it can be close to 0, but it's not going to be 0. Okay, if this is equal to 0, thank God. Now, I don't think you have a system where the error is equal to 0. Okay, there's no perfect system. All right, so once we are doing the projection, we can go ahead and find the error. And if you manipulate your vectors, you end up getting this. Okay, you end up getting this as you are. This is our ultimate goal. Okay, we manipulate that, we end up getting this. Now, if you keep manipulating, that means here we expand, you end up getting this. And when you rearrange it, we come back to the same equation, which is what the normal equation, where you saw this to be our A and this to be our P, which is our A, X is equal to what? B, right? Now, this, our X, can be solved when we invert our vector, and that is what is being done over here. Okay, that is being done over here. But one thing is that the columns, they have to be linearly independent. You saw this thing already. They have to be linearly independent, or else we said you have 3 solutions. Either you get a unique solution, which, as I said, if you are getting 0, that means it's a perfect, but hardly you can get as close enough to 0 because of the error, or you're going to get several solutions, or you're going to get no solution. You have to make sure that your columns are linearly independent. Okay. So, Albert, are you okay? Hello, Albert.
Yes, sir.
Okay. So let's
Hello.
pick your pen and paper, and let's try to do this right now. Then I think that is my last slide. Okay. Then we. Emmanuel, you said, I should give a practical scenario. That is what I've given. So here, pick your pen and paper. We are all going to do this right now. I don't know the answers. We are going to work it together. So here, let's assume I have a data. Okay. And I'm going to do some prediction. So my feature 0 here, 1 here, then 2, and my target, which is 2, then 2, then I think 2.5 again, right? All right. Now, we are using linear regression, okay? So we are going to determine which our y, which is equal to what? Our f of what? X. That means if I put in any value, maybe 3, or let's say even 5, my model is supposed to give me an answer, right? Which we saw that it can also be written as ax, which is equal to what? B. And we saw that our A is this, okay, this, and our B2 is this, and our X, okay, is equal to our theta, right? Okay, so this is what you guys are going to do. Now we are going to get this for me right now. So first, what is our X? First, what is our Y? So let me create a pool. Once I ask the question, then we start doing the calculation. Okay. So what is capital X? Capital X is equal to, then small y is equal to. All right. So let's be quick. I'm waiting. Let's be quick. What is our X? What is our Y? Now here, remember the X is our matrix, right? The Y is our target. Okay. So what is our X? What is our Y? If you want me to go back, I can go back to show you some of them. Okay. So a practical scenario. I'm here. Okay. All right. So this is my X. This is my Y using this data. So they gave me this data. Okay. So this is the data that I have. I'm giving you a similar one, right? So this is the data. So from this data, I wrote my X and also my Y. You get it? My X and my Y. Remember your X, you're having a constant term and the other variable, and your Y is your target. Okay, so let me go here and you type in your, okay, so this is our data point now. So I need my X, I need my Y. All right, so you type your answer, you click. Hello guys, I'm waiting on. Let's be quick, eh? Or you don't get me. Are you confused? Let me know. Can you hear me? Okay, so Esther saying okay. Uh, okay, so all right. Please participate. I just want to know, Ima, if you're on the call, make sure you participate. Make sure. Just want to make sure you understand. Okay. Okay. So Albert. Okay. Okay. Precious. Your ex is only two responses. Okay. Albert. Your Y two. Okay. All right. That is okay. Who is this? Oh, okay. Maybe you guys are confused. Okay, so here your x is going to give or is going to be 1. Okay, 1, 2, 3. So it's going to be 1, 1, 1, right? Then 0, then 1 again, then 2. This is going to be your x. Okay, this is going to be your x. So this is the constant term. And these are your variables. These are variables. So the variables, these are the variables. So this is your x, this is another x, this is another x. But if you're coming out with the matrix x, we need a constant term. Without a constant term, it will be difficult for us. Okay. All right. So are you okay? So this is my x. Please make sure you are others. I have to make sure you guys are all okay, please. So this is my x. This is my constant term. This then my y, right? Okay, precious, go on.
Yeah,
Or
please.
it's a mistake.
The y is 1, 2, and then 2.5.
Okay, 1, 2, and 2.5, right? Okay. All right. So this is it. Okay. All right. So what are we going to do next? Now that we know our x, know our y, we can calculate for this. The transpose of the x multiplied by the x itself. So go ahead and do the calculation. So if you transpose x, all this, you know how to do the transposition. Columns becomes what? Row, right? So here becomes 1, 1, 1, then 0, 1, 2, then it will multiply the x itself, right? Which so is also 1, 1, 1, then 0, 1, 2. Now this, we learn how to multiply this, remember? We learn how to multiply this, remember? So what do? We
One time.
said you use the 1, 1, this, then you can use the next one, which is 1, 1, 1 here, right? Then you also have the next one, which is
0.
uh 0, 1, 2. Okay, please go ahead and work it and give me the answer. Okay, then here too is what? 0, 1, 2. Okay. Okay, so go ahead, work it and give me the answer. Be quick, be quick, be quick, be quick. All right, so can publish this. All right. Then the next one is um, which is x raised to the power t and x itself. All right. So hurry up and get me the answer. Okay.
Hmm.
Please, you are going to get a matrix. Oh, we learned this, right? This
Yeah.
matrix is what? 2, 3, and this one is what? 3, 2. So the dimension is going to be 2 by 2 matrix. So please make sure you give me a 2 by 2 matrix.
Mm.
Okay, I think I'm supposed to make it a column and a row instead. So that or this will make it a little bit this one. Supposed to be the column. I said a column, I made it a row rather. Which is 1 0 here. Okay. Then to multiply I think 1 or 0. Am I correct? Okay. Okay. Okay, so all right, so let's be quick. I don't want to waste time. Okay. So the answer is yes. Yeah, so some of you got it, which is 3 3 3 5, right? Okay, so that is that. Now go ahead and do this. The transpose of the x and the y. Transpose of the x and the y. The transpose of the x and the y. The transpose of the x and the y. Which is x transpose and y. Okay, so the transpose of the x and the y. All right, let me wait for two more people. Manal. Okay, no, Ima has given the. Okay, then who again? Godwin. Okay, let's see. The last person, then I can proceed. Okay. So, wow. Okay. All right. So the correct answer is immense response. So uh, the correct answer. So the first one we have three, then three, then three, five. Right. That is for this. Then the B, which this one, which we use B for it. Okay. So this one is my 5.5. Sorry, no minus 5.5 and 7. All right. So you didn't get that. Please make sure you do the calculation here. Godwin, he had 4.5. You made a mistake. Check your calculation well. All right. Please, those of you who didn't get it, make sure. So here, when you transpose the x, you use it to multiply the y. The y is this. Okay. So we've transposed the x. This is something that please. Okay. So these are things that when you are doing your presentation, you should, I mean, we are not asking you to teach us, but these calculations, we should, find some of them in it, okay, so that we can follow and do it to make sure that your model is actually doing whatever it's trying to do. All right, so now that we are done, we need to multiply this, as you can see over here. So, what we are doing over here, we can find the inverse of this, then we use it to multiply this, okay. Used to multiply this. All right. So we already know this. So let's find the inverse. The inverse, you can find it, right? So how do you do that? We have, we want to find the inverse of whatever you've done, which is this one, which you guys got this. Then the determinant, this and this will give you 15. 15 minus 9 is what? 6, right? So 1 over 6. 1 over 6. Then we will swap this. So we have 5, then 3, right? Then we negate this one, which is minus 3, minus 3. I hope I'm correct. Okay, the inverse, because you need to find the inverse as you can see over here. Then we use it to multiply our answer again, which is what? 5.5 and 7. Okay. All right. So please go ahead, do this calculation right now. Then after that, you tell me the answers. So you're going to get two values. One of them is going to be our theta 1. The other one is going to be our theta 2. All right. So I'm giving you guys, it's 9 o'clock. Let's be quick. Few minutes. Try to complete this so that I can put the answer inside. There we go. All right. So what is theta 1, theta 2? Okay, you can give it to me as fraction, or you can also give it to me as decimals. Okay, so let's be quick. Okay, our time is up. I have to go and rest. Oh. All right. So theta 1, theta 2. Right. So theta 1 is equal to and theta 2 is equal to. All right. So you can give it to me in fraction form or decimal, any of them. Let's be quick. Then we can end the session. All right. So I can see Albert 12, 13 over 12. 13 over 12 and 3 over 4. Three over 4. Then Gordon also had, wow, okay, okay. All right. So that is that. Okay, so uh Albert, Gordon, Richard, and Emmanuel, and I think Awudu also came out with yes. So that is the answer. Please, if you do not do the calculation, do it. Okay, I'll publish and you see the solution. Okay, so when you when you take the slice, okay, make sure you go through yourself so that you can work them yourself. Okay. All right. So please, this is where we end today's session, right? This is where we end today's session. If Gary, next week we'll start with eigenvalue and eigenvectors, where it's very, very simple. Where when you do the transformation, we want to get back to the same vector again. So we are transforming this vector, but we want to get the same vector. We don't want to get a different vector. That is where the eigenvalue and eigenvector comes from. Okay. So next week, Saturday, the lab is going to be based on this. Make sure you don't absent yourself. And Emmanuel, I hope you are okay. You now understand? Is it clear? Do I still have to give you